semester, I have decided to increase my office hours from 3 to 5 every Monday and every Friday, because basically I'm there about 2 hours. So what's the point of not making it official? So I'm going to be there 2 hours there, but this is done intentionally just to help you with the project. And I want you to get help from me, because otherwise you'll find it kind of difficult by yourself. So you need to get help from me, and I've extended it from 3 to 5 on Monday and Friday. And I will change, also update the syllabus for the course with this new office hours, so that you know exactly when it is. What was that?
Is that today also?
Yes, today as well. Especially today, because we have missed already the one on Friday, this coming Friday. So we need to have more office hours. And for the past month, almost, I have always had 2 hours office hours every week. So that's not a big change for me. So what I wanted to discuss today was a really cool problem, and that's what we'll try to solve today. And hopefully, if we are done with it, we'll go to other problems. So this is problem 3, simulating a fun Monte Carlo game. So some of you might have seen this problem before. So we have 3 doors. This is actually a game that apparently it's a show that was aired like 50 or 60 years ago. So a long time ago. And the problem was something like this. Back then, nobody knew about the statistics and Monte Carlo simulation. So nobody had a clear answer, and this problem has been around for about 50 years. So there was one last paper on this topic, on this problem, in 2016. I found it accidentally, that somebody had just tried to summarize all the conflicts and arguments that exist on this problem, and still people are arguing it. So the problem is this: we have 3 doors. Behind one of them there is a car, and behind the 2 others there are goats. Okay, so now the host of the show asks you to pick a door, and you choose one. Okay, and then the host says, okay, you have, for example, you picked 1, and the host says, okay, I'm going to open one of the 2 other doors for you. So I'm going to eliminate one of the choices. So he eliminates, for example, 3. He opens it, and there's a goat behind it. Now he asks you again, are you willing to switch your choice to another door, to the other door that exists, or not? So the question is now, what would you do? Would it be to your advantage to switch, or to stay with the choice that you made? Or should it make any difference at all? How many say we should switch? Okay, how many say we shouldn't? About a little bit less than the other group. How many say it doesn't matter? Okay, good. So that's the purpose of this problem. We're going to find out if this is really true or not. But I think we have the majority as to switch. It would be the correct answer. But I think probably that part of it is because, some of you have seen this problem before. But why is it so? So the truth is that, let me tell you the truth. The truth is that when the host, the truth is actually more complicated than that. So all of you were correct in a sense. So what you missed in your question, which you should have asked further about it, was whether the host opened this door intentionally, knew, for example, that there was a goat behind it, or he just opened the door randomly. It could have been a car. Okay. So the true and the correct answer is that it depends on the knowledge of the host. So if the host knew already that there was a goat behind the door and he opened the door for you, then you should make your choice. Switch your choice. In that case, you will have more probability to win. Not necessarily always win, but you will have more probability of winning. But when the host doesn't have any knowledge of what's behind the door, for example, if he opens it and there's a car there and the whole game is ruined, then that doesn't make any difference because the whole game is ruined. No, it's not because of that. It's just because there is a little bit of math behind it. So let's think about it this way. I'm not sure if I have this one. No, I don't have the solution here. But can somebody provide an answer for why? Let's assume that the host knows what's inside of this door. He knows that there's a goat here, and he opens the door and shows the goat to you, and then he asks you which one you want to pick. You want to switch or not, right? But now the question is, why is it to your advantage to switch the door to the other one? Yes.
It's my understanding when you first pick the door, you have 1 in 3 chance of getting right.
Right.
Sort of in one of them down, which one's that 1 and 2,
Very good. Yes. Yes. So the argument is that initially you didn't know what door contained the car, right? So how much probability do you have to pick each one of these, and that would be correct door to get the car? It's 1/3, right? So each door has an equal probability of 1/3, right? Now, the host opens one of the doors for you. Let's say you picked 1 and the host opens 3. Okay. So what was the original probability that the car was in these 2 doors? 2/3, right? But now the host has given you some new information. And that new information is that this door, so between these 2 doors that contain 2/3 of the probability of winning, one of them has been eliminated. One of them is empty. So all of that probability, all of that 2/3 probability concentrates on this door. You still have 1/3 on this one, but all of that 2/3 probability is now focused on this door. So you will have 2/3 probability, 2/3 chance of winning if you switch to this door. So that's the argument. But we can show that if the host opened the door without any knowledge of what's inside of it, then it wouldn't make any difference. So on average, you would the same amount of time, the same number of time as you would switch. So now our goal in this problem, I don't know if that was clear for all of you. Was it understandable for why you win more often if you switch? The reason is that, again, because there's 2/3 of probability in the 2 other doors that you have not chosen, and then once the host eliminates one of them, the other door contains 2/3 probability still. Yes?
Why wouldn't it just become 50-50 at that point? When it's still on the door closet.
Good point. So it would become 50-50 if the host opened the door without any knowledge of what's inside of it. But when he knows, for example, you see there is a bit of information, extra information that is added to problem once the host opens the door. And that bit of information is that the host knows which door contains the car, so he will never open the door that contains the car, right? So that extra piece of information leads to the concentration of the probability to the door that you have not chosen. So we're going to show this by simulation. So again, you choose this door. Every door has 1/3 probability. So if you have chosen this door, you have 1/3 chance of winning. But these 2 doors together have 2/3, right? Now this just frees the problem at this point. So we have 2/3 on these 2, 1/3 on this one. Now the host opens one of these 2 doors for you. These 2 that have 2/3 chance. So what happens? Nothing else has changed. So you still have 1/3 here, but for these 2/3 probability that you had originally, one of them is eliminated. So that 2/3 chance still exists here, but all of it is now focused on one door. So you have 2/3 chance on this door, 1/3 chance on this one, as you had originally. Right? It sounds a little bit weird and strange, and just to give you a relief, 93% of Nobel Prize winners made the wrong choice. So they said we shouldn't switch. So if you made a mistake, you're with the 93% of Nobel laureates. So don't worry about it. So it's a tricky question, but now what we are going to do is to show that the correct answer is really to switch. That is, if you switch, you will win more often, twice as much than when you did not switch. So one of you asked a question. No questions? Okay. So now, my question is, how would you simulate such a question, such a problem? So the simulation basically means a recreation of the reality, a recreation of an experiment that you could do in a physical world, but now in a computer. What's the benefit of simulation? The benefit is that you don't need to bring a host here, pay him like $5,000, and you don't need to have a show to prove something to other people, and a lot of other things. But more seriously, if you go to your industry job or academic environment, there are a lot of things that you cannot do in physical world to get the outcome, to see what the outcome of the experiment is. For example, you cannot blast a nuclear bomb to see what the outcome of it is. You have to simulate the result. At least in the 20th century, you cannot do it anymore, hopefully. So there are lots of other things. For example, you cannot blow a bridge to see how strong it is, right? It's impossible. So you have to have other ways of testing whether your bridge is strong enough against an earthquake of magnitude 8, right? So you would have to simulate the conditions of the bridge, and then simulate an earthquake that comes and tries to destroy this bridge, and then you see how strong your bridge is. Okay, and that's exactly the same kind of thing that we are going to do here, simulating this experiment of opening the door. So what is the problem? The statement of the problem is that we have 3 doors, and then we want to pick one door randomly. Okay. A lot of you ask me, like, when you're given a problem, you don't know how to start solving it and attacking it. So what you need to do is to understand what the problem says, what are the given conditions in the problem, and what you want to get out of it, right? So what are the input information in this problem? So the input information is that we have 3 doors. What else do we have? You pick, yes. So 1 car behind one of the doors. And that's randomly there, right? And then 2 goats behind the 2 others. The other information that is that you pick 1 door randomly. So what other information do we have? We have the host opens 1 door randomly for you. Well, not the one that you pick, some other door, right? So host of the program opens another door. What does he know? He said?
No, I'm saying so he doesn't know.
He doesn't. No, he knows what door you chose, but his own choice to open for you will not be the same door as you chose.
No,
Okay.
I'm saying he doesn't know what he has.
No, he knows.
Oh,
He knows. So he will not open the door that contains car. Okay. So that's something that we have to also consider in our simulation. So now, what should we do? What should we do in order to simulate this? So here's the thing. With just one time repeat of this experiment, you will not be able to see whether you will have more chances of winning by switching or not, because just one experiment is not enough. You could lose in the first round, but over time, for example, if you repeat the experiment 1,000 times, then you will see that on average, you have twice chance of winning compared to when you did not switch the door, right? So these are the conditions of the problem. Now we would like to simulate this problem and see what is the chance that we win. So in order to calculate the chance, what is the chance? What is the definition of probability chance? Nobody tell me. It's not the number. It means the number of times you have won something divided by the total number of times you have tried it, right? So if you want to calculate the odds of winning the car by not switching, then it would be no switch wins. So suppose we repeat this experiment 1,000 times, divided by total number of experiments. So the total number of experiments, for example, could be 1,000 here. And then this part, if we are right, if our argument is correct, we said you would have one third chance of winning if you don't switch, right? So this number should be around 333 times if we repeat this experiment 1,000 times, right? So overall, it gives you 1/3 chance of winning. Okay. So now let's try to simulate this game. See if we can solve it. Again, we need to do this for as many times as we can so that we can see the average behavior, not just one experiment behavior. Because in one experiment, you either win or lose. Even if you switch, there's still a chance that you will lose. But the point is that if you repeat this experiment over time, over a long period of time, so many times, then on average you will win if you switch. Okay? So now let's start. If you want to simulate this problem, what do we have to simulate then? We need to simulate doors, right? So we have 3 doors, and then what else do we have? We have cars and goats, right? So one problem in simulation is that everything has to be represented by numbers. So there is no physical entity that we could say this is the door. So we have to represent the doors by their numbers. So what I would do is that I would go to here, and then I say I have 3 doors, right? So I'd say doors is equal to 1, 2, 3. Okay. Now, what else do we have? So I would call this Monte Carlo. That's the name of the show. Okay. What else? So we have one card behind one door randomly. How do we assign random numbers? So we want a random number between 1 and 3. So we want one of these doors randomly to be chosen and then assigned a card to it, right? So I say door containing oh, that's just too lengthy. So door with card is, so how do we generate random numbers, if you remember from last time? In random integers. Rand I, right? Or Randy. So, yeah. So, Randy 1, 2, 3. I think this would give you, I always forget the syntax. That's why I don't want you to memorize things, because I cannot do it myself, so you're lucky.
Just 3 is behind. You can do just the math.
Oh, with 3? Okay. Because I don't remember if this gives you a matrix of 3 by 3 or what happened? Copy and then paste it here. Okay, yes. So it gives you a random number. Yes. So door with car is a random number between 1 and 3. And door with goats, we know what they are. If you know where the car is, the 2 other doors do not contain the car. So we have to also determine those 2 doors. So now let's see. Let's wait a minute. What do we want to do? We want to pick also one door randomly. So let's pick also one door randomly by the guest. So it's say my choice equals a random door, right? And to pick another random integer from 1 to 3, I just say rand 3. Okay. And then the host has to choose another door, right? Which is not my choice. Okay. So my choice should not be among the doors that the host wants to pick, right? And it should not be the door that contains the car. Is that correct? Yes? Okay. Because the host wants to open a door that contains a goat, and it's not my choice. Okay. So if you want to determine the choice of the host, what should we say? You should somehow eliminate these 2 numbers, door with car and my choice, from doors, and then create another list that contains either two numbers or one, right? So let's say my choice happens to be the same as the door with car, right? Then the host has two other doors that are goats. So he has to choose between the two. He could just pick one randomly, right? Because both of them have goats, so he could just pick one randomly. But when my choice is not the same as door with car, then how many choices the host has to open? One, right? Because one has the car, the other one is my choice, so there remains only one door that is goat and doesn't contain the car, and it's not my choice, right? So he has to pick that door deterministically. There is no option there. Okay, so now with this problem, we have to create a list of doors, because sometimes the host has two options, some other times it has only one option, right? So we have to create a list of the doors from which the host can choose, right? Can pick. So we could say, how do we create a list? How do we eliminate? So now the problem is we want to eliminate these two numbers from this list. How can we do this? So here's one way of doing it. We could use the logical indices. If you remember, for example, we have doors equals to 1 to 3, or we could make it actually a vector. We don't need to make it a cell array. So let's see. Doors, no. Let's save this. Okay, so now I say doors is 1 to 3. Yes, what was that? Raise this one, you mean? Oh, I'm sorry. Okay. Okay. Now we have doors equal 1 to 3. Now what I can say is that I say doors, if I want to choose something inside doors that's not, for example, let's say we want to eliminate 1. So I want to get all doors that are not equal to 1 from this list, doors. So how would I do it in MATLAB? I can use logical arrows. I can say, give me the door elements where doors is not equal to 1. So what does this give me? So this should be a square, not a parenthesis, not a square bracket. So let's see what this is. So you see, I'm trying to print the elements of doors where doors is not equal to 1. What does this mean? What will it give me then, you think? 2. It will give me 2 and 3, right? Because there is only one element that is not equal to 1. So let's do it. Let's first print this and see what this is. So doors is not equal to 1. So it's going to give me 0, 1, and 1, right? So it says doors in the first element. So if you look at the values of doors, it's 1, 2, 3. When I say doors is not equal to 1, I'm comparing a vector to a number, right? So it tells me it's not, the first one is 0, the first one is 1, so 1 is not equal to 1, so that gives me 0. The two other ones are not equal to 1, so that gives me 1. Okay, so now if I say doors of this, then it's only going to give me the elements that are not equal to 1. Okay, so is that clear for all of you? Do you see what I'm doing? If you have problems, if you don't understand it, ask it right now, because that's the time to ask questions. No questions? Is it clear? Okay. So now, let's go back to our original problem. What do we want to do? We wanted to pick a door from this list, 1, 2, 3, that is not door with my car, that is not my choice. So how would I do it then? Any suggestions? Okay, a little bit louder, because that's correct. Doors, and then doors not equal to what? Not equal to, let's first eliminate the door with car. Okay, because that's definitely not the choice of the host of the problem. So the host choice, I would say the host choice is this. Okay. But then, if you do this, sometimes it's going to be two elements, not just one element, right? Because if these two are the same, then the host has two choices. Okay. So now let's try this once and see what we get. So I'm going to show it to you that the host choice is going to be sometimes one element, some other times two elements. You see, this time, what was that? Oh no, that's right. Yes, I haven't eliminated the other one. Yes, you're right. Okay, so I went too far. So here's the thing: we have eliminated one door, the door that contains the car. Okay, and that makes sense because let's see what the door with car is. So that's number 3. So the host choice reduces to 1 and 2, right? But that's not enough because we need to also see what my choice is. So let's see what my choice is. It's also 3. Okay, so the host really has 2 options left. Yes.
Since both of the random permutations, since we didn't like reset one of them, aren't they always going to be the same?
Good point. So yes, so we could, the thing is that whenever you restart MATLAB, the random seed is restarted to the default value. So every time you open MATLAB, you're going to get the exact same results as you got last time. In order to resolve this problem, you could add RNG, and then you say shuffle. What this does is that it sets the random number generator SID for rand I to the CPU time, I think, as far as I remember. And the CPU time is something that just goes on forever. It just adds, so it becomes a bigger and bigger number, right? So it's never the same thing as you last time ran your MATLAB, unless you manipulate the time of your CPU, of your computer, and bring it back to the some old time. In that case, it would
Will both rand I's be the same though, or does it?
No, it will be different. There's no worry. Even if you don't have RNG shuffle, you will still get different numbers every time you run rand 3. But the problem is that if you restart your MATLAB, reboot it, and then run this code again, you're going to get the exact same sequence of random numbers. So here, you see, every time I run, I get a different number. But since the options are very limited, you will get a lot of same numbers every time. So you see, for example, I'm getting a lot of 1s, and now I get 3, 2, 1, 1, 1. Again, a lot of 1s. Okay. It's not because the random number doesn't work. It's because my choices are limited. It's 1, 2, and 3. Okay. So now we have to remove the other choice. So we say the host choice is this. So now let's remove the other one also. So I say the host choice is this. Instead of door with car, we're going to remove my choice now. Okay. Now here is the problem. Host choice, I made another mistake. So now it's correct. And this is host choice. You see why I made the change? Does it make sense for you? So I defined a vector containing the host choices with the door with the car out of it, right? Now I have to eliminate my own choice from the host choices. So I say host choice, I modified it to something new. I say the host choice is the host choice where it is not equal to my choice. Okay. Now, so what do we get so far? Let's try it and see what we get. There is still a problem. So what's the size of host choice at the end of this code? Not necessarily. It could be 1, it could be 2. When is it 2? Yes. No, the second one right here. Sometimes it could be also 2. Why? Why could it be 2, you think? When my choice and the door that contains the car are the same. So suppose I pick door 3, which contains the car. Then the host of the program has 2 other choices to eliminate, right? 1 and 2, right? So there's still a problem. if the size of host choice, let's try it and see if we can get a case where the host choice is not just one element. So this time it turned out the host choice to be one single scalar. Try it another time. This time it's now 2. You see? So sometimes it could be just one scalar value, door number 3, but some other experiments it could give you 2 doors, 1 and 3. So the host has to pick one door randomly at this point because both of them are possible. Both of them contain goats, right? So now how do we pick this door? How will we do it then? We have done it already in the code. Exactly, yes. So what I would do is that I would say host choice. Well, we have to pick one of the 2 elements, right? So I could say I want a random element. So the host choice is the host choice rand I of 2. Does it make sense for you? So what I'm doing is that I'm picking a random number between 1 and 2. Well, here's the problem. This code will lead to a problem, to an error. What is the error? If it's just one, if it's already one door, then this is going to give us a problem. So let's try it and see if it gives us a problem or not. Well, this time it worked, but another time, please. Okay, yes. So we got the error. You see, index exceeds matrix dimensions. What does this mean? It means that the host choice here was just one door. So we cannot pick one element from one element scalar value, right? So we have to add an if conditional here. Does it make sense for you guys? So I say if, how do we check for the size of the vector? Length, we could use length, right? So I could say if length of host is not equal to 1, end. Okay, so that would make sense, right? Or I would say I could also equally say equal to 2, right? Because we have 2 options. It's either 1 door or 2 doors, right? So I could say if it's equal to 2, then it would be actually more. No, it doesn't make any difference. So it does actually, I think. So if you're really a high performance programmer, then you would care to make a difference to write this as this one or as an equality. So equality would be a little bit faster, just a tiny bit faster. Yes?
Rand I could do a random number, either 1 or 2.
Yes.
What if there's only choice is 3?
No, we are picking the element. So see, so the host choice could be anything. Could be. So here's the thing: the host choice is either a scalar or a vector of 2 numbers. We don't care what the values of those numbers are. We want to pick one of the 2 elements, one of the 2 numbers, without caring about their values. Yes, Jack. We would say rand I of what? Or the host choice? Yes, I think that would be a more robust code. But then here's the thing. If we have more than 2 options, that's good. That's, I think, clever. So what Jack is suggesting is to remove these 2, this if block, and then instead of rand I of 2, say rand I of length of host choice. So we say length. You see what we are doing? I think that's a clever idea. So let's try this. So you see what this change has done to our code? So if I remove this, now instead of having the if block, I get a random number from the length of host choice. So the length of host choice could be either 1 or 2, right? If it's one element, then I pick the first element in the host choice. If it's 2 element, then 2. Yes.
Would that take any extra time because they have?
Yes, it takes a little bit more time. It leads to a more concise code. That's right. That's another good point. But it will take more time. But for our problem, it doesn't matter much because the code is really fast. But in a real scenario, in a real larger scale simulation, you're going to care about these things because the random integer generator takes a lot of time. It does a lot of calculations behind under the hood. So you have to keep that also in mind. So 2 ways, either if block or the method suggested by Jack. So either of them is useful. Now we have built the host choice. So this is the host choice. This is my choice. Door with card. Now what do we need to do at this point? So we want to, what do we want to get? Should we stick with our door or switch the door? Which probability should we calculate? Okay, we can calculate. It doesn't matter which one because the other one is can be obtained from the other one, right? So we could try the probability of switching. Okay. So the host has eliminated one door for us, and now our problem is to switch to another door that the host did not pick, right? That makes it a little bit difficult. So how do we find the other door? We could calculate the other way. We could say we stick to our own choice and let's see how much probability is of winning we have in the end, right? That would be one possibility. We could also switch the door. So let's try the easier way first, which is sticking to the same door, not switching. Okay. So then what I can do is that I can say, but so far we have done this only. So what I do is that, so I say I want to calculate the number of times that I have won this game, right? So how do I calculate it? I have to define a variable at the beginning. I say win counter, okay, and I set it to 0. So initially I haven't won anything, and then I want to repeat this experiment a lot of times, right? So I would say let's try this experiment for n experiment equals how many times? Let's say we want to try it 1,000 times. Okay. Okay. So now I have to we have to create a loop, and each time count the number of times we win or we lose, right? So we have to put all this experiment again in a loop. So what we have done here, so this is the experiment that we have done so far. That gives us the choice, the probability of, so at the end I could say if, so I made it a little bit confusing. So let's forget about this part first. You don't need to remove it, but I'm going to show you the result of one experiment. So I say if my choice, we want to see if we won this game or not. If my choice equals door with car, then print okay, end. All right, so now we can run this this code and see if we won or not. Is yes, without switching doors. Yes. So, but we could also, well, we don't want to print that. So I would say else. What should we say when you lose? No. Okay. Right. Okay, so let's try this and see what we get. Okay, we lost. So we can try it another time. So one time we have run the experiment, one loss, right? Second time. So let's count the number of wins that we have. I'm going to run it for 10 times and see how many times we win. So 1, and then we have 2, 2, 3, 3, 3, 4, 5. It's really difficult to count. So let's really run the experiment. But you see, you get a lot of no's and a few yays, right? All right. So now, what we want to do is to automate this process of repeating the experiment instead of just pressing the F5 button to run the experiment again and again. So how do we do this? We define a loop. So I say, we want to make these choices every time I run the experiment. So I say for I, you know, I don't like the word experiment. I like sample because I'm sampling the experiment, right? So I say I sample, and I told you whenever I use I at the beginning of a variable, I most often use it for loop indices. So I most often stands, I and J stand for loop iterators. Okay, so I say 1, 2, and I name this n sample, so of the number of experiments that I want to run. Okay, then I press tab for these, shift them forward, and then say end this loop. Okay, now instead of this printing yoo-hoo and nice, so I want to get a little bit more informative message. So what I would print here is the number of wins that I've got. So how do I calculate the number of wins? I have to accumulate the number of wins that I've had, right? So I have defined a win counter and the total number of experiments, right? So I say win counter, if I win, set win counter to win counter plus 1. Okay. If I lose, then just do nothing. We don't care. So let's remove the else statement. We care only about wins, right? And then at the end of the for loop, we could also display the number of wins that we have got, the odds of winning. So total wins by not switching. But the total number is not really informative. We want the odds, we want the chance, right? So what should we do then if we want the chance? Divided by the total number of experiments by that time, right? Not by n sample. We want to divide it by I sample. So we will see odds of winning by not switching. Okay? Yes, so the problem wants you to do something more than this. The problem wants you, the homework question wants you to also plot the results in the end. But plotting is really easy. So once you have got this, what we could do instead of defining a character, a win counter like this, we could define it as an array, right? That tracks all the wins for each experiment, up to the experiment. So then we want to plot and see, given the number of experiments, how many times did we win. So I will let me try this first and then see what we get, and then I will plot the results for you. So I say num to str win counter divided by what? Can someone tell me what? I sample. Right. So now we are done. Let's try this and see what we get. Okay, you see? So if I go to the top, initially, we probably got some highly varying numbers. So you see, wow, we started with winning totally the game. So initially, the number of wins was 1. So we won the first game, and we had 1 experiment. So the odds of winning was 1. The second experiment we lost. So the odds of winning became half. The third experiment, so we did 3 experiments, and we won the third one again. So win, lose, win. The result is 2/3, right? And 2/3 is 0.666666 whatever, right? So, but you see, as we go and we repeat more this experiment more and more, we converge to a number which is very low, and that's around 0.31, which is about 1/3 chance of winning, right? But we could also switch this and see, calculate the odds of winning by switching, which is easy. You can just implement it yourself and see the results. But I'm going to show you how you can plot this if you wanted to plot the results. So I would say something like this. Instead of defining a win counter, I make this a win sequence. Okay. We could just define it as zeros of what size it should be. How many elements does win counter have? N sample. Yes, that's correct. So that's why I ask you always to define values in variables, because that makes your life much easier. So I define win counter as an array, and then I fill the elements of win counter. So I say it's all 0. Then I say win counter I sample equals win counter I sample plus I sample minus 1. Is that correct? Yes. So at each moment, so we have to add one more thing here. I say else. So if you have won this round of experiment, then add the previous number of winnings to the current one, which is 1, right? Else, if you haven't won, just set this to the previous number of wins, and do nothing more. Okay. Now, what else do we need to do? I think we forgot something. This code still has a problem, because I sample when I is 1, then I minus 1, 1 minus 1 is 0, win counter is not defined. Index of 0 is not defined, right? So we have to think of a solution for this problem. I could add this. I could add this and say the for loop starts from 2 and goes to n sample plus 1. So the same number of experiments again, but the 0th element of win counter is basically the first element of it is 0. Okay. Now we have the code working. So I have created a sequence that contains all the number of wins by the total number of wins that we have had so far. And then, one thing more. We don't want the counter. We want the odds of winning. So I would say odds of win. So I will change all of them. If you press Shift Enter, it changes all the names to this. Now we want to save the odds of winning, which is what? Which is, so this is the total number of wins that we have had. So we could do it in another way. So we could say we could have a win counter, and then we could have also odds of winning, which is the result of win counter divided by the total number of experiments. So odds of winning, odds of win equals, and this should also be plus 1, because we have now, we did just a little bit of extra things for nothing. So the odds of win is this, and then at each time the odds of win is this. Odds of win of I sample equals win counter I sample divided by I sample. Right? Does it make sense for you? No, I sample is 1. It always starts as 1. So I sample is the number of experiments that we have had so far, right? And the odds of winning is just the number of times we have won the game divided by the total number of experiments up to that point. But win counter is already the sum of wins. That's correct. So I did one thing is stupid, and that ruined the whole fun of this Monte Carlo simulation. I did not to define an array of win counter. Win counter could be just a scalar. So instead of this, I could just say win counter equals 0 and remove this line, because the thing that is an array is the odds of winning. That's what we want to keep track of. We don't need to now count the number of wins. We want the odds of winning to be a sequence so that we can plot it, right? So win counter is not an array anymore if I want to do it in a more appropriate way. And this is now correct, and I don't need this else statement again anymore. So this is what I said. If we win, then I set win counter to one more number of wins, and then I define odds of winning to be win counter divided by I sample, right? And now I don't need anymore this extra index going from 2 to n sample plus 1. So now this should work. We can try it and see. Instead of printing win counter divided by I sample here, I can print the sequence, and that should give us the same result, almost. Okay, you see? So we ran the game again. So this time we are printing the odds of winning, and that's 0.32. Now I can plot this. I can say, go to the end. This is the last thing we're going to do, and I have to leave also myself. So I say the odds of winning, plot odds of win, all of it. That's it, as simple as that. Now let's try this. That's not good. We don't like it. Why is it so? Odds of win. Oh, I think I see what the problem is. So you see, whenever we don't have my choice equal to door with car, the odds of win is set to 0. It's already 0, right? That's not the case. So if the choice is not the door containing the car, then the odds of win should be set to the previous value. Okay, that will solve the problem. So now, again, sadly, I have to go back and modify this. We go from 2 to 1. Okay, now this should solve the problem. Let's try it again. Yes, you see? So we start from 0 this time, and the odds of winning gradually converges to about 1/3. If we run this experiment again, we get a different plot. The one thing that we can do is that we can set this to a logarithmic axis so that we get something like this. So I can say set the current axis x scale to be log. So now this would solve the problem, and I set the line width to 3 and color to red. Okay, one last run and you have a great weekend. Okay, at least it worked. It shows the plot. So you can do the same thing for the odds of winning by switching, and then you will see that the result there would be 0.66 instead of 0.33.